Okay, so I want to spend a little more time talking about resonances. Um, we saw before, we saw the tube that is closed on one end and open on the other. Well, on that case, we have at this end we have the node, and then at this end we have the antinode. You can think of it as the wave is locked into this position, but over at this position it's not. It's locked into this antinode. Now we called these the fundamental first, second, and third overtones, but we're actually going to now call these, just get some slightly different notation, and we'll call this the first harmonic, the second harmonic, the third harmonic, and on and on. And these are told by the number of quarter wavelengths. So with the first harmonic, we have one quarter wavelength. With the second harmonic, we have 3 quarter wavelengths, because this is the next available number of quarter wavelengths that you can have in that tube. And then on and on as we go along. We derive this expression to give the frequency of each particular harmonic. So as you squeeze more and more quarter wavelengths into this tube, then you increase the frequency of the sound that you get. Okay, so now let's look at 2 different other scenarios, and these are going to look different, but they're going to be the same. We're going to look at a pipe that's closed on both ends. Now, really what we're dealing with here is a string, because you can't really close a pipe on both ends and get a sound out of it because you can't have any airflow through it if it's closed on both ends. So we're really talking about a string, but we'll imagine that it's instead a pipe that's closed on both ends. But you really want to think of it more as a guitar string. And then we'll also deal with a pipe that is open on both ends. Now, if I draw my waves, I get a node on this end, and I get a node on this end. So this is going to be my first harmonic, and over here I get an antinode on this end. Let's see, I get an antinode on this end and an antinode on the other end. So in both cases, my wave, or the length of my pipe, gives me a half wavelength. So the length here is equal to 1 wavelength over 2. All right, 1/2 wavelength. So I have 1 times lambda over 2, and then also over here it's going to be the exact same. I get 1 lambda over 2. I can fit in a half of a wavelength. Going from here to here is a half a wavelength. Now, if I fit in a second harmonic, it's going to look like this. And here I get in a full wavelength, or I'll call it 2 half wavelengths. And then in a similar way over here with the closed pipe, I get I get 1 wavelength here, 2 wavelengths here. So my full length of the pipe is 2 half wavelengths, 2 lambda over 2. And you can imagine it goes on and on. In the next pipe, I'll have 3 half wavelengths. In the next pipe, I'll have 4 half wavelengths. And my resonances will increase in frequency, or I'll cram more and more half wavelengths into each pipe as it gets a higher and higher resonance frequency. So we can develop an expression for the frequency for both of these, in fact, and it's going to be the same, and that is that the frequency for each harmonic is going to be N times V divided by 2L. You should be able to see how this comes about, right? That L is equal to 2 lambda, or excuse me, L is equal to N times lambda over 2, N lambda over 2 for each harmonic, letting N be equal to 1, 2, 3, and on and on. Notice that this is different than it was for the closed and half pipe because of the nature of that. Because I was looking at quarter wavelengths and I was locked into a node on one end and an antinode on the other, my integer values were 1, 3, and 5. Here I go 1, 2, 3, and 4. Now this will be on your equation sheet, but just make sure that you're aware of the differences between the closed pipe, open pipe, closed on one end, open on the other end, and then these 2 scenarios. All right, so back to what we were doing here. So if L is N lambda over 2, that means that lambda is, what's that, 2L over N. And if I want to know my frequency is, what is it, V over lambda? Yeah, that's right, V over lambda. So that's going to be N over 2L times V. So notice that's this expression right here. And this is the frequency for the pipe that's closed on both ends. Although really, just to remind you, we're really talking about a string suspended between 2 points, and then I get these resonances, like a guitar string, for example. In fact, if you play the guitar, you probably know that you can get different resonances by not fretting the string. That is, don't press the string all the way down to the fret, but you hold your finger lightly on the string, not pushing it down to the bridge, but if you hold your finger down to the string lightly, then you can get those resonances. And some guitar players will actually play those resonant frequencies on the string. It's a different kind of sound. Okay, what's it? Who is that? I think it was like Guns N' Roses or somebody. There was a guitar player that used to do that. All right, y'all probably don't know who Guns N' Roses are, but anyway, you can play these harmonics on your guitar as well, which is different from playing higher notes. It's a different kind of sound. Okay, so I think that's it for harmonics. Make sure you're aware of how the harmonics fit into the different pipes, and then also how to calculate the frequency for each of them.